is Stephan Winnerl from Dresden. He will speak about unusual Coulomb effects in graphene.
Thank you, and thanks to Klaus for getting us together here for this nice meeting and giving me a chance to present our results, and also thanks to the local organizers for their hospitality. So for this talk, I will take you away from ultra cold atoms to hot electrons in graphene. Here's an outline. I will give a brief introduction into graphene in general, and then talk about 3 topics related to Coulomb interaction in graphene. And to those, I will give an introduction at the beginning. The first one is a double-banded saturation behavior if we optically pump graphene. The second one is an anisotropic carrier distribution and its relaxation to an isotropic one. And the last one is Auger scattering in Landau quantized graphene. So what's special about graphene? Graphene is as all of you for sure know, is a honeycomb lattice, a single layer of carbon atoms, and it has a peculiar band structure that does not exhibit an energy gap. So the conduction band and the valence band touch in so-called Dirac points, and the dispersion is linear in this relation. So this is very different from conventional semiconductors like gallium arsenide. And also in this region, at fairly low energies, up to like 2 electron volts, the dispersion is linear, the system is isotropic, and there's perfect electron hole symmetry in the system. What are the relevant energy scales in graphene? Optical phonons have a fairly high energy, 200 millielectron volts, and the Fermi energy, well, that depends on the sample, basically from 0 to around 400 millielectron volts. So the mid-infrared and far-infrared region is actually a perfect probe for the natural energy scales in this system. And we will mainly use the free electron laser at Dresden-Rossendorf to probe effects in graphene. So the question is, how does this peculiar band structure, how does this affect the ultra-fast dynamics? What is unique about graphene, what you don't see in other systems? So this, of course, is of fundamental interest, and many people have contributed to the knowledge in this field. One question that still remained and that we wanted to tackle is, can we disentangle the carrier-carrier and carrier-phonon scattering? Because both of them are fast on a sub-100 femtosecond time scale typically. So is it possible to disentangle them? And of course, these results are important for optoelectronic devices like fast detectors, modulators, saturable absorbers, devices that people have demonstrated on graphene. So here is a cartoon-like sketch of various interactions like carrier-phonon scattering, carrier-carrier scattering, intraband type, so just within the conduction band. And here we have a Coulomb process where one electron relaxes down here in the conduction band and brings up another carrier from the valence band. So this is impact excitation, and the inverse process would be Auger recombination. So I will, most of the talk, this process will be the most relevant one, but also this one will, because it's in direct competition, this will play a role. So Coulomb scattering in general in semiconductors, maybe it often seems a bit boring. I mean, it thermalizes the distribution. It establishes a hot Fermi-Dirac distribution from a non-equilibrium distribution, and it's often kind of featureless, whereas scattering with phonons, you often have replica and have some structures. Coulomb scattering often call it a bit boring, featureless. And what I want to show you is that in graphene, there are some features, there are some particular features about Coulomb scattering. And those are of very different nature, but you will see that during the talk. The experimental technique we are using is pump probe spectroscopy and 4-wave mixing, but in this talk I will focus on the pump probe spectroscopy, where we excite the sample with a strong pump pulse, and then a probe pulse is used to measure the transmission of the sample. And what this typically does in graphene, we excite carriers from the valence to the conduction band when there's Pauli blocking for the probe beam, so the transmission shoots up and then on a characteristic timescale relaxes down. And we use photons in a very wide energy range from around 110 millielectron volt to 1.5 electron volt, and we use different sources, in particular the free electron laser. One very brief word on the samples we are using. This is not the Scotch tape exfoliated graphene that many of you may know. It's large area graphene on silicon carbide, and actually it's a multi-layer sample. It's grown on, so this is the structure of silicon carbide. It's a Wurtzite structure, so there's a silicon terminated phase and a carbon terminated phase. And on the carbon terminated phase, if you heat the sample up to like 1200 degrees Celsius, the silicon evaporates and it starts pushing out graphene layers. And interestingly, these layers are twisted rotationally against each other and only weakly van der Waals spawn. So they essentially behave like individual graphene layers. This has been verified by many techniques. And this is important for many of our experiments. The majority of these layers is almost intrinsic. Only the ones close to the interface are doped. So this is the kind of sample we will be using. Now let's get started with the first topic, the double-banded saturation. If, as an introduction, let's look at a two-level system. Let's look at the population dynamics in a two-level system. If we weakly excite this system, so initially most electrons sit in the ground state, and then the occupation of the upper level will be proportional to the intensity. There will be a linear relation. If, on the other hand, we strongly excite the system, then we'll reach a state where there's half filling of the upper state, if the degeneracy is the same, and then the sample is completely transparent because there's the same probability to absorb an extra electron or to have stimulated emission of one, and then the sample is transparent. So this is a textbook example for the lab-matter interaction, and the occupation of the upper level is given by this relation, where I is the intensity and IS is the saturation intensity, which is a characteristic measure for this banding here of a saturation curve. And this saturation intensity depends mainly on the scattering rates in the system. So graphene is, of course, very different from a two-level system. It's continuous band. So what does this have to do with a two-level system? Well, let's just very naively look at some experimental findings. These are results we gathered over several years with different photon energies, and we measured the induced transmission, which is proportional to the occupation of the level where we excite the electrons to, and we measure it as a function of the fluence. I use here the fluence, which is the pulse energy divided by the area instead of the intensity, because the pulse duration is different. So, but in a sense, this is very similar, the intensity and the fluence. So we see we can fit this data quite well with this relation. So is this by chance, or is this maybe a leaky two-level system? And it's interesting if we plot this saturation fluences versus the photon energy. So we have data here over 2 orders of magnitude, and they lie around a quadratic dependence here, and also results from other groups lie well on this line. So is there something behind that? Is that telling us something? Well, in graphene, the density of states is proportional to the energy. So there's a linear relation. So if we would think that carriers sit in occupy just the states where we excite them, then we may expect here a linear relationship because the absorption in graphene does not depend on the energy. But we see the quadratic one. Well, we could get a quadratic one if we say the system instantaneously thermalizes, or thermalizes faster than the pulse duration. When we fill some space here in the conduction band, and this would give a quadratic relationship. So maybe this is pointing into this direction. So, and since these pulses were really on a picosecond timescale, this probably is true, but the system thermalizes faster, and we essentially deal with a hot Fermi Dirac distribution. So is that everything? Is that nice, but maybe kind of boring? But it's not the whole story. So to go beyond that, we used short pulses, like 30 femtoseconds, and a photon energy of 1.5 electron volts, and we find this saturation behavior at the high fluencies. We basically reproduced the results that Ted Norris and others had seen before. So this is well known. This is the Pauli blocking at the high fluencies. But interestingly, we saw at 3 orders of magnitudes lower fluencies, where you would expect a perfect linear relation, we also saw some saturation behavior, and it fits to the same function. So what is that? What causes that? Well, luckily, we have a good contact with Ermin Malic and his students, and he said, well, can you calculate that? Well, this is really puzzling. So they applied the density matrix formalism, like what Ermin showed on Monday for the 2D materials. There it was on an excitonic basis. Here it's just electrons and holes. Solve a semiconductor Bloch equation, and they find the same thing. So they find the saturation at the high fluencies, the Pauli blocking, but also at 3 times lower fluencies, they see such a saturation-like behavior, a deviation from the expected linear relationship. How can we understand that? Well, here's a naive experimentalist picture on that. Imagine a small bucket. This should be the optically addressed states in the graphene. And because we have Coulomb scattering, when we fill these states, let's make some hole in this bucket. And then it's sitting in a larger bucket, which should be the whole conduction band. And now we pour water into it, which should be indicate the occupation in this inner level. And you see we fill it up in a stepwise version. And here you can look again at the filling of this inner level. So it first goes up, when it saturates. When it again goes up, when we start backfilling into it. So you see our naive model gives us this double saturation thing. What does that have to do with graphene? Well, the microscopic theory shows that exactly such a thing is going on. So at very low fluencies, we just occupy the states and have a linear increase of the occupation here. Then Coulomb scattering sets in and scatters carriers out. And at some point, at some intermediate fluencies, there's also significant backscattering into these states. And then the occupation goes up again until we have basically full Pauli blocking of the optically addressed states. So with this, the first story is ended. So we see this double banded saturation behavior, and it has to do with the intensity-dependent scattering rates. Its Coulomb scattering is just dominant, and it depends on the excitation density. Now you may ask, how general is that? Is that graphene specific? The honest answer is we don't know really. We looked in the literature and didn't find that people reported it for other systems, but we see nothing really graphene specific in it. So it should be also present in other systems, given that the Coulomb scattering is the predominant channel, because this would be intensity dependent. Probably for a system that has like strong Fröhlich interaction, probably there it's much more difficult to see. Okay, and as a final remark, this saturation can be used in saturable absorbers for short pulsed lasers, and graphene is attractive because it's a very robust material and works for many frequencies. Okay, now the second part is the optically excited anisotropy and its decay. In the Dirac cone of graphene is isotropic, therefore the linear optical properties are isotropic. So if you look at the absorption, it does not matter in what direction with respect to the crystal lattice your light is polarized. But if the nonlinear properties, if we strongly excite it, then the polarization of the light breaks with symmetry and the occupation looks like this. So there's a node in the occupation in K-space just in this direction of the driving field, and there's maximum occupation just perpendicular to it. This actually was first predicted for graphite by Dresselhaus just 1 year before the whole graphene excitement started. And so they say that the existence of a node in the absorption coefficient as a function of K is a special effect and has never been observed in other materials. And they go on saying, nevertheless, it might be difficult to observe the existence of such a node in the optical absorption of graphite experimentally. So this is a challenge, we should do it. Huh? And we didn't do it in graphite, but in graphene. So here are the results. We pumped the graphene with linearly polarized light, and then we probed either parallel or perpendicular with parallel or perpendicular polarization. And the results you see here, so if the probe beam is parallel polarized, then the Pauli blocking is much stronger, more than 2 times stronger pump probe signal than for the perpendicular configuration. And the theory from Ermin and his colleagues are in almost frightening agreement here with the experimental results, considering the fact that they don't have any fitting parameters. So it's a real microscopic theory. But you see the anisotropy is present, but it vanishes quickly. Basically, after 150 femtoseconds, it's gone. Then these curves are perfectly on top of each other. Now, the theorists can do one very nice thing. I always envy them for this. They can switch on and off with individual contributions. So here you see the angle in K-space. So this is the initially optically excited excitation. And if there's carrier phonon scattering only, you see it quickly, after 50 femtoseconds or so, it goes to an isotropic distribution. Carrier-carrier scattering, on the other hand, this rapidly redistributes carriers here at a certain angle. It leads to a Fermi-Dirac-like distribution for a particular angle, but it does not scatter efficiently across different angles. So very different results for carrier phonon and carrier-carrier scattering. Now, can we do something like that in the experiment? Well, obviously, you cannot switch on and off one interaction, but we can try to strongly quench the distribution from optical phonons by going to low excitation energies of our photons. Just not give the phonons the room in energy to be emitted. So let's try that. So now we use photons of an energy of 88 millielectron volts. Before it was 1.5 electron volts. And you see qualitatively the same behavior, strong anisotropy, but the scale is completely different. Now we see this anisotropy on a picosecond time scale. So it lives much longer. It works, we see that. And we did a control experiment, a two-color experiment. Again, we probe it with 88 millielectron volts, but we excite up much higher. So we give the electrons the room to emit optical phonons here. And you see the data a bit noisy, but nevertheless it's clear that there's no anisotropy visible. So the phonons here really destroy the anisotropy, whereas in this case we basically switched off the contribution from the phonons and look at the pure Coulomb scattering, and this preserves the anisotropy. So this is an interesting result because in the graphene community, thermodynamic model, which was probably best formulated by Dmitry Turchinovich, this is extremely successful to explain many phenomena. You say, it thermalizes quickly after 100 femtoseconds, you just have to deal with a Fermi-Dirac distribution, and the system forgot at what energy it got excited. This is true for many cases, but here you see it's not true in general. The system here definitely did not forget how we excited it on a picosecond time scale. Okay, well, why is Coulomb scattering preferable collinear? Well, this is very simple. Just look at this. If you move along a line here on the Dirac cone, then due to the linear dispersion, you fulfill energy and momentum conservation just easily in this two-particle scattering process. And it's not the only way you can scatter, but this you can do for many, many carriers, and all the other processes are just less probably. For example, if you have an initial state here, and here you scatter this one out like this, and this one inwards like that, then you also fulfill energy and momentum conservation. And here is the matrix element for the interband Coulomb scattering, so where these angles enter here, so it's just the highest probability for collinear scattering and backward scattering, so an angle of 180 degrees here. This process is forbidden. So we changed the fluence over a large range here, more than 2 orders of magnitude, and you see that initially we have this for small fluences, this anisotropy is very pronounced, and then it goes down, because if we excite more carriers, we have more Coulomb scattering, and by this we also have more non-collinear Coulomb scattering. The temperature, I don't want to go into this detail. On the other hand, it does not have a strong influence. So it's really the Coulomb scattering that is dependent on the fluence. I want to give you also a microscopic equivalent to this. This is in Berlin Wannsee on a sunny day. The Berliners get excited by the optical excitation, by the sunlight. They line up here at the pay booth of the lake. So this is highly anisotropic. But if they are behind there repulsive interaction, so they have a isotropic distribution. But you can do something if you give them a preferential direction. If there's a race, then they move much faster in this direction, and this preserves the anisotropy. So this is the macroscopic equivalent to our process. So let's conclude with the second part. I showed you that linearly polarized light in graphene leads to an anisotropic distribution in K-space, and this is well preserved by Coulomb interaction. It's only the phonons that lead to a rapid isotropic distribution. And it's an interesting finding because it shows that the thermodynamic model is not the full story. Often you really need to look at things on a microscopic basis. So the last part is devoted to Landau quantized graphene. So if we put graphene in a magnetic field perpendicular to the layer, the linear band breaks up in a series of Landau levels, and for a conventional two-dimensional electron gas with a periodic dispersion, this would be just the equidistant series of a harmonic oscillator. In graphene, it's much different, where the energy of a level scales with both the square root of a magnetic field and the index. So we have this non-equidistant ladder with a zeros level at zero energy, and then here's the valence band and the conduction band states. The optical allowed transitions, they change the absolute number of the index by plus or minus 1. So like this, there's always a pair of transitions that can be distinguished by circularly polarized radiation. So Landau quantized graphene has been studied for a long time. Basic transport experiments started initially after the finding of graphene, and a lot of static spectroscopy has been done, but dynamics was basically unexplored. There was one pioneering experiment by Paulina Blochoczka in magnetic fields of 8 Tesla, but this was excitation basically in the quasi-continuum of states with an index of like 100. We, in contrast, want to focus on these lowest levels here, on the individual levels -1, 0, and 1. And for this, we do pump probe spectroscopy with circularly polarized radiation in all four combinations of pumping and probing with sigma plus and sigma minus radiation. So the sigma plus will pump this transition, the sigma minus this. So what do we expect for the pump probe signals? Well, if we pump and probe with the same polarization, we expect just bleaching. It's the normal Pauli blocking. If we pump this one and probe this one, well, then this one will fill the initial state of a probed one, so this should increase the absorption. So the rule is simple. For same polarization, we expect a positive pump probe signal induced transmission. For opposite polarization, a negative signal corresponding to absorption. And the whole world will be fully symmetric with respect to sigma plus and sigma minus because of the electron hole symmetry. If the system is really intrinsic. If it's slightly doped, this breaks the symmetry. Nevertheless, this rule, same polarization, positive sign, opposite sign, negative pump probe signal, this will always hold. So this is the only thing you have to remember. Now, for the relaxation, what do we expect? Well, there should be Auger's type Coulomb scattering processes as indicated by the green arrows here, and then some relaxation via phonons, but since we're not resonant with an optical phonon level, this is probably of minor importance. And in the microscopic theory, this was introduced only phenomenological at this stage. By now, there's also microscopic theory for this, but it's not important at this point. We're mainly interested in the Coulomb distribution, in the Coulomb scattering, which is in already at this stage microscopically. Okay, here I show you the surprising findings for two of these combinations, namely for pumping with sigma plus radiation. So we pumped with sigma plus and probed with sigma minus. So we would, opposite polarization, we would expect a negative sign, but we saw a positive one. And the theory also predicts the positive one. So this is quite surprising. And then for the same polarization here, pumping with sigma plus and probing with sigma plus, initially we see a positive signal, which is in accord with the expectation, but then it swings over to negative. So this is also strange. But again, there's a very good agreement between experiment and theory. So what's going on? Well, let's look at the level occupation, what the theory is telling us. So we pump this transition, and then we look at the occupation of these 3 lowest levels. And you see the occupation of the first lambda level shoots up. So this is surprising because we don't pump into it. We just pump this transition. So this Auger processes brings up efficiently carriers into this first level. And then for the zeros level, it's maybe even more surprising. We pump into it. Initially, the occupation goes up, but then it goes down. So this is like if tonight at the dinner you have a nice caipirinha and somebody's pouring it in, but the level gets lower in the glass. So this is, you can attribute this to strong Auger scattering then. So here it's going down, and because of this process. If we, again in the theory, switch off the Coulomb interaction, then you see the boring expectation that we pump here. The first level is unaffected because nothing gets up here. And then the 0 level, the population is increased by the optical pumping. So very clearly this, the Coulomb scattering dominates the response here. If we switch off the phonon interaction and just look at the pure carrier-carrier scattering, it looks quite similar to the full response. So the occupation of the first level goes up, of the zeros goes down. The only difference is it stays there. And this is quite clear because the pure Coulomb scattering cannot bring the energy out of the system. It just goes into a new hot equilibrium state and stays there forever. And here finally a picture that maybe makes it intuitive why we have this depletion of the zeros lambda level. Think of slightly n-doped graphene, which we have in our case here, and here is the Fermi-Dirac distribution. So if we heat it up and we smear out the Fermi edge here, at 0 energy, the occupation will go down. And if we translate that into the lambda quantized case, it just means that the zeros level will be depleted in the thermalization process. These findings have triggered a number of theoretical investigations on lambda level lasers, which is an old dream of a solid state community, that you have a laser where you can use the magnetic field to adjust the frequency. And so far this has not been realized, and now there are a number of proposals. I don't want to go into detail into them by various groups that show that this lambda quantized graphene indeed is a promising material, but one has to be very aware of this Auger scattering, of course. If one chooses a very naive regime, then this Auger scattering will destroy the population inversion. Also, carrier multiplication is possible. This may be another interesting application. So the conclusion of the last part is that a strong Auger scattering can actually deplete an optically pumped level in lambda quantized graphene. And we see this very directly by the sign change of a pump probe signal. And what I didn't show you, but it's confirming these results are recent 4-wave mixing experiments where we see the rapid dephasing. And the population dynamics may be interesting for these tunable lambda level lasers, and the 4-wave mixing indicates that it's a tunable nonlinear material that can be used in nonlinear optical processes. With this, I'm at the end and want to show you the overall conclusion. So we looked at 3 very different but phenomena, but that all strongly related to Coulomb scattering in graphene. One was with double saturated saturation, the anisotropy and its decay, and the scattering in the Lambda quantized case. With this, let me thank all the people who contributed to this, Martin Mittendorf and Jakob König-Otto, the PhD students who did most of the experiments at Dresden-Rossendorf, Ermin from Gothenburg and Andreas Knorr and the students, they were extremely helpful with the microscopic theory. And we had some collaboration with Milan Olita and Marek Potemski for static magnetospectroscopy, and we got most of our samples from Claire Berger and Walt de Heer from Georgia Tech. With this, let me thank you for your attention.